Thank you very much to everyone for being here, both in person and online. Today we have the distinct pleasure of having Professor Pizzuto from the University of Liverpool. Gabriella is a fellow of the Royal Academy of Engineering and overall a rising star in the robotics and applied robotics and chemistry. So we're very, very happy to have her here. And without further ado, Gabriella, the floor is yours.
Thank you so much, Michele, for the invite. It's really great to be here. I got my PhD here almost 6 years ago now, so it feels like home. So hopefully I will share some of the exciting research that we've been carrying out at the University of Liverpool. I'm currently on a joint appointment between computer science and chemistry. So my talk will hopefully explain or introduce some of the challenges we have in deploying and developing robotic chemists. And that will be kind of the overall talk, I guess. And again, I recently started my fellowship now almost 2 years ago, so I will be introducing some of the works and some of the open challenges we have within this field towards what I like to see it as upskilling our robotic chemists towards having them carry out more scientific discovery experiments. So just to put some scene, because I also come from a robotics background, and I assume that most of the audience have never been to a chemistry lab like me. So just to introduce this, chemistry labs over the years have been very manual. So a lot of the experiments and a lot of the reactions are carried out with manual experiment, I think. Yeah, oops, sorry. Maybe I can remove this one. Okay, let's just put it in that. So over the years, you can see a picture of more than 100 years ago, and chemistry labs look very similar, especially in the early stage materials discovery. As a roboticist, I feel like that's disappointing on what we have done as roboticists. So what are the challenges and how can we transform these chemistry labs? And just to put into perspective, this picture and the one over the right is from our Materials Innovation Factory at the University of Liverpool, which is one of the most advanced AI-driven chemistry labs in the world. And still, a lot of the early experiments are done manually. So, of course, the world is not that bleak. Self-driving labs are becoming more popular, and there's also a lot of interest and need for deploying these systems in labs. So I like to see it as the three wave of robotics and chemistry. So we have automated platforms, which are very good at doing a very specific thing. So they are good at, for example, in that chem speed, solid dispensing, liquid addition, heating and stirring, but all of it is contained within the same platform. Then the second wave were the introduction of industrial robotic manipulators in a very sterile environment. So the robotic manipulator has some solid addition and liquid addition in front of it, and an analysis instrument at the back. So again, we have a more modular station, but this is more with industrial robots. So the robot is not collaborative. And I think the third wave, or what I am excited about and what we are doing at the University of Liverpool, is deploying our robotic chemists in human labs. And we're not just deploying them in human labs, but they're also driven in the first one, the mobile robotic chemist back in 2020 was driven by an optimizer. So there was a problem, a photocatalysis problem, where the robot was optimizing different parameters within the chemical space. And then this was driving the experiment. And this was able to run for continuously for 7 days. And again, I come from a robotics background, so deploying a robotic system for 7 days in an academic lab is a huge, I think, achievement. And following that, we also at the University of Liverpool deployed also a multi-robot system. So you have different mobile manipulators interacting with each other and other instruments. And in this case, in the bottom video, the decision-making was done jointly with humans. So these are kind of the recent advancements in the field. I will still argue that we're still not there yet. So we have done some experiments with these robotic systems, but there's still plenty of challenges, which I'm very excited to be able to get the chance to solve. So just to give a brief overview of how this looks like, usually you have an optimizer. So this can be a Bayesian optimizer. Nowadays, it's also potentially using AI models like large language models, and that are driving the chemical space. So we're optimizing a computational model on the chemistry side. And then the robotic experiments, which are carried out by some of our robotic systems, are more lower level experiments. And together, this end-to-end system is able to carry out different experiments in the lab. So this was kind of the idea for the mobile robotic chemist. And I think in previous editions, you have had some colleagues of mine like Xenophon and Andy to talk a bit about this. But what I think is really more important is we need to bring in the human scientists, and we need human input at all aspects of the experimental stage. So when it comes to the human input on the optimization and AI models, I think maybe you're familiar with some of the work done in Liverpool. So this could come in terms of constraints for the experiments. It could come as experimental design. So this is a ongoing research within Andy Cooper's group on using humans and AI to drive the experiments. And on my end, what I'm really interested in, how can we use humans to work closely with robotic systems in terms of running the robotics experiment? So what is the role that the human scientist can play? It can, again, this is all quite new research direction. So I would say there's different factors that this could come in. So it could be, for example, through giving demonstrations to the robot. It could be through giving oversight, especially when we work in safety critical environments. If there is some uncertainty experiment, potentially delegating that to the human to make the decision. Again, this is very much an open problem. I imagine that the future of materials discovery will be very much human in the loop, human-centric, and hopefully also as part of self-driving labs, but I think the role of the human is really, really important. So in terms of, I've already introduced robotic chemists. What is the current gap between robot chemists and humans? So if we look at some of the systems that we have deployed at the University of Liverpool, you will realize there is a common trend. Robots are mainly used for sample transportation. They move our vials or our materials around between different stations. But if you study a bit what human chemists are capable of, it's much more advanced. It might look, I think for chemists, these are very simple tasks. To me, as a roboticist, they look very advanced. So the way that human scientists use different glassware, use different tools, they're able to handle different materials. Just to put things into perspective, materials in early stage experiments look very different, and sometimes they're very unpredictable, especially when exposed to environmental conditions. So when I saw how human chemists are carrying out experiments in labs, it was very obvious to me that these are very highly dexterous tasks. And for the robotics people in the room, I think we would all agree that dexterity is an open problem in robotics. So how can we get to minimize the skill gap? How do we get our robotic chemists to move closer to what human chemists are doing so effortlessly? So this was kind of the motivation for my research and the fellowship that I'm currently working on. So I proposed this idea of laboratory skill acquisition. So how can we get our robotic chemists to learn new skills that would enable them to do more than moving samples in the lab? And what are the challenges there? So traditionally, lab automation, for those of you who might or might not be familiar, is a very much open loop system. So the robot will carry out the experiment. There's a lot of engineering effort involved, but it doesn't really adapt. It doesn't get feedback. So how do we embed this, and what are the challenges in doing this with robotic chemists? So kind of the first research direction that we started working when I started my fellowship around 2 years ago was how do we get laboratory motor skills? And in this aspect, I will introduce some of the kind of recent work we have done, and also hopefully show the challenges there as well in terms of getting robots to be able to handle different materials. Then I will just give a quick overview on where we would like to go towards having safer robotic chemists. So when we deploy these systems in human labs, we need them to be able to detect failures, recover from failures, and also to carry out their procedures in a safe way. And again, when we think about safety in robotics, we tend to think about more how robots collide with humans potentially. But in a chemistry lab, the risks are very different. The chemicals that we have, we might not understand what are the risks with them. And if we do understand, it might not be the same risk that we have for humans. So what are the challenges there, and how do we get to think about how we get robotic chemists to work safely? And a more recent, let's say, we just started to think about is how do we get human chemists and robots to collaborate together within the same lab. So far we've been mainly focusing on deploying the systems in human labs, but how do we get them to work there? So again, I will talk mainly on the laboratory motor skills today, but I'm very happy to talk after about the second part of the research. And then just to talk a bit more on the laboratory motor skills. So the kind of goal would be that we would like robotic chemists to handle any material. So when we synthesize materials, and I will explain a bit more for those of you who might not be familiar with that, can have different properties. So how do we get good models of these materials so that our robot could be able to understand how to interact with these materials? We would want the robot to adapt to new experiments. So it is very common that it's very common that different chemists carry out experiments in a different way. So how do we get the robot to adapt to these different experiments? Laboratory environments might be semi-structured environments, but they're still very different. So we need to deploy these robotic systems in different environments. And while I would argue that glassware is to some extent standardized, there's still enough variability with different glassware that the robots need to be able to handle. So that's the ultimate goal. And the spoiler is that we're not there yet or anywhere close to be able to do all of this. And towards trying to advance some of these, we've been looking at two main case studies and trying to understand the challenges within them. So these are powder weighing, so very simple, like you're baking a cake, you start weighing different sugar, flour, and whatnot. So that's kind of what we would like our robot to do in a lab. And for the robotics task, that means that the robot is manipulating unconstrained materials. So the material is in a container without any constraints. And then or like has physical constraints, but not within the glassware. And then the second part, we'll talk a bit about autonomous sample scraping, which means that the material is within a glassware, a vial, for example, and how do we retrieve this material within this vial. So just to give some background on powder weighing. So this was the first skill that we started to think about, and the goal is very simple. You want to weigh different materials with high accuracy and minimum failures. Again, I like to see things in like the three waves. So you can have a platform like the ChemSpeed, which can weigh different materials. You can understand what are the advantages and disadvantages of using this. Then you have something which is in between. So you have a robot arm interacting with the solid dispensing, so the Connect XPR. And some of the work we've been working on is how do we get robotic manipulator, so a more general purpose robotic manipulator, to weigh different samples. And kind of our argument towards this is that, first of all, the robotic chemists can be more modular. So weighing solids can be one of the different tasks, but even beyond that, we could be able to adapt to different materials. We could get some feedback and inform what the robot is doing as well. So there are different reasons why we were thinking about it like this. So in terms of learning powder weighing task, powder weighing is a long horizon task, so I would focus only on the powder dumping first, and then I will talk a bit about some of the challenges with the other parts of the task. So it's a very simple robotics problem. You have two robot actions. These are in continuous space. So the robot adjusts the pitch of the tool and also shakes the tool. So those were the simplest kind of way to do the task. The observations in this case, again, we wanted it to be simple. So you have the target weight and the current weight that you get from the scale, and also the robot state, which the robot knows where the tool is. And then the robot needs to get as close as possible to the target weight based on the current weight. But in this formulation, and this was initially done by the lab in Japan, it was that there was no particle simulation and no material information. So the robot is learning to do an action without any understanding of what is the material or any representation of what the material is in its spatula. So the way we started to think about it is that, okay, robotic action is very simple, but material dynamics are very hard. So modeling the dynamics in materials is really hard. And why is this so hard? Because you get different materials that could range with properties like crystalline materials, which are sugar and salt, and then more cohesive materials like semolina and sodium bicarbonate. So the complexity of this means that you have different physical parameters that you need to optimize and try to get the robot to learn an action based on these parameters. And the other thing to this is that different materials, when exposed to real-world conditions, could potentially absorb water. So that changes the properties of the material as well. So not only material dynamics are really hard, robot-material interaction is even harder. So how do we get the robot to have control system to be able to weigh all these different materials with these different properties? But if we look at some of the very interesting work in human cognitive science, it is believed that as humans, we tend to predict the dynamics of, for example, fluids or materials that interact with through approximate simulations. So we tend to have a good intuition of how the material will behave. So we were thinking, can we give an approximate model to the robotic chemist based on a similar approach? So what the robot really needs is not to understand how cohesive a material is or how adhesive the particles are, but what it needs to understand is to be able to adapt its control action based on one potentially property or the minimum amount of properties. We know that materials flow differently. So flowability, and I will show some examples over here. Oops, okay. I think that made my laptop go crazy, but yeah, so different materials flow differently. You can see materials like sand, which can flow very well, and other materials like flour or something similar that have less flowability. And if you have noticed also between the simulation and the real world experiments, there is also a simulation to reality gap. So you can see how the cones form in both aspects, and they don't form the same. So beyond the fact that materials behave differently, it's really hard to simulate them as well. So that means that the underlying physics models and the simulation could potentially not be as accurate as we would like it. So we started to think about how do we map these material flow behaviors to physical parameters that are available in the simulation. So for the roboticists, maybe you are familiar with the NVIDIA Isaac sim, and these have different particle simulation that you can use, and you can set different properties. But the different properties you set in your simulator might not necessarily match with the real world materials that you have. So you might be simulating, for example, in our case, we wanted to learn a policy of the robot learning how to weigh different materials, but what it's learning in simulation will not transfer, and this will probably increase the simulation to reality gap. So we wanted to optimize the materials that we were having in the simulation to train the policy with real-world data. So we did this in a very standard way. We used an optimizer, Bayesian optimization, and we found a calibration task, and I will explain a bit more. So this calibration task was a task that gives us an estimate of the flowability, and then we optimized the parameters theta that could relate to the physical parameters within our simulator. We had to minimize the error between the real-world task and the simulation task. The challenge was, how do we find a good suitable task that will represent this flowability in terms of our materials? Thankfully, there's people in material science who have already studied this. So there is a very simple test, which is basically pouring the material and then measuring the angle of the cone forming. And depending on the angle, it shows whether it's good or it's poor or good flowability. To be able to have this and feed this data into our simulator, we created a very simple robotics task that is matching what we have in simulation. And as you can see in the results on the slide, the automated measurement, which was with the robotic system to get the data of the materials, was more or less similar with, of course, some standard deviation with the manual method. So in the end, we concluded that this way of measuring how materials flow is a good representation to be able to feed into our simulator and improve the way the robot is learning the powder dumping policy. So we got our flowability data, and we have these parameters that now we can feed into our simulator to change the physical parameters to match the real world. So this was the method that we have proposed. So in the first part, you can see the calibration task. So you do the task with the robot, you transfer this to the simulation, you minimize the gap between the parameters and the simulation and the real world, you get the optimized data set, you use the data set to train your policy. So our intuition was that if materials flow more, we think that that is easier to be able to weigh different materials than those that are more cohesive. So our intuition was that having a robot trained with easier, more flowable materials would be better than having a randomized data set. And then once we got the policy, we transferred this on the real robot and we evaluated the system. So this shows some of the examples. So you can see the task that was in simulation and also the task in our real world setup. We tried it with different configurations. So one way of doing it is to randomize everything. Domain randomization is one of the most common methods. However, there are physical parameter configurations that in the real world will not happen. So for example, increasing gravity to within the range doesn't make much sense. So we wanted to constrain this such that it matches our physical world. We also tried some ablation studies. So we did the curriculum learning method. And in this case, we also reversed the curriculum. We thought maybe we're wrong. Maybe giving the robot more flowable, less flowable materials would actually help or not. So we also checked that. And in the end, we saw that using this learning approach of introducing materials in a structured manner helps the robot to learn a better policy. And so the interesting thing and what we wanted to achieve is while we tested with these materials are representative of different materials you could find in the lab. So some materials would be more crystalline and some materials would be more like sodium bicarbonate, so more cohesive. So we looked at materials that were not exactly tested, so slightly out of range, and also different target weights as well. So after that, so that was only a part of the problem. So as I mentioned, this is a very complex problem. So when you weigh materials, you don't just shake material outside of your spatula. You also have different steps. So you'd scoop the material, you would have motion planning as well, and then you start to dump the material. So we've also started to think about the other steps, and there are different challenges. So if you break the problem down into different aspects, there are different challenges, but I will not talk a lot about that today. But one of the most obvious challenges we saw was that when we have robots interacting with materials, are we using the right tools? So for example, we started by using a spatula because that is what we think what we know human chemists are using. But we know that a robotic manipulator doesn't have the dexterity of the human hand. So are we really using the right tools? We know that humans try to use the right tools for the right task. So I'll give you an example of eating a plate of spaghetti, and you wouldn't use a knife for the spaghetti. So you would eat it with a fork. And as humans, we tend to use the tools to extend our manipulability. So we should really think of doing the same with our robotics manipulators. If we just give tools that have been designed for the human hand, maybe that is suboptimal. Maybe that is not the right way of looking at the problem. So we started to think a bit about this. We had some preliminary results where we tried different spoons and we got different results. Some of them are a bit more obvious than others, but we still don't know if this is the right approach. So what we're interested in now is how do we choose the optimal tool for the robot to be able to handle these different materials. And then also, of course, it's a very complex problem. So you also have to think about what control primitives. So for example, we simplify the action space. Do we need a more complex action space? Then we also have the representation of the material. Again, we're assuming that having this flowability measurement is good enough, but is that really helpful for these new tools? And again, so this is a kind of ongoing discussion between robotics people and chemistry people, I would say. So roboticists tend to like their systems to generalize to as many things as possible. Chemists like, at least the ones in Liverpool, to have a system that works very well almost all of the time, even if it does not generalize to everything. So where's kind of the trade-off between this hardware specialization and generalizing to different materials and different tasks? So maybe is it the right tool? Do we need a range of tools? These are some of the open challenges. And we've just started a project a month ago, actually, so through APSRC. So we're starting to study how we deploy these robotic chemists with these tool task policy adaptation. And we're working with one of FK's former people, Kevin Luck, who works in co-adaptation of different robot bodies. So I don't have the answers to these questions yet, but hopefully in a few years, I would be able to have that. Okay, so I started with the first skill. Then I would like to introduce you to the next part. So for me, it was, I think, very interesting to understand how we deploy robotic systems in chemistry labs, because it is very different to how roboticists tend to tackle the problems. So one of the projects when I joined Andy Cooper's group was this ERC Synergy grant, where we were trying to think about a workflow and experiment that involves multiple robots and multiple stations for handling solid state chemistry. As roboticists, at least how I was doing it, we tend to focus on one single skill, and that's mainly how my talk would look like. But having this understanding, I could see that there are different challenges. So for example, in this multi-robot workflow for solid state chemistry, the robot goes to an automated platform like the ChemSpeed. It takes the materials, which are all in a vial, and then it transports them to a station where there's a dual-arm robot. The dual-arm robot uncaps them, puts them on a grinding station, puts them on a grinding station. It grinds the sample, so it breaks up the crystals. The crystals stick on the plate, and then it transports the plate to the analysis instrument. But again, as I mentioned in my previous slides, there is the challenge that in this case, the robotic mobile manipulator or dual arm manipulator does not handle the materials. So there is no direct material manipulation. So one of the challenges in terms of this aspect, we are relying that the grinding station would transfer, without even manipulating it, all of the crystals onto the cap. So what were the challenges? What if some material remains stuck in the vial walls? So we started to think about how can we get the materials that potentially have taken days, maybe weeks to synthesize and are very expensive in terms of time and money. So in terms of retrieving materials, this is how the manual procedure looks like. Again, human chemists do this very easily. It's just vertical motion, so super easy. If you think about it from a robotics perspective, it's a force task. So the robot needs to scrape the vial wall, depending on different materials. Some of them dislodge faster than others, and it needs to maintain contact within a vial wall. And you can maybe use a force torque sensor or force feedback to be able to get a better understanding of what you're interacting with. The challenge is always the same. Materials are always very different. So some of them can be more like slurry, like pizza dough, and it slides very easily. Some of it can be more powdery, some of it more crystalline, so you need to apply more force. So how do we go about tackling this? So I will introduce a two-level controller. So we wanted to rely on a Cartesian impedance controller because of its compliance. So we wanted to command the torque that the robot is applying, and this is composed into three aspects. So you have the Cartesian impedance controller that is for the compliance of the torque. Then you have the null space torque, which is there to avoid singularities and joint limits. And finally, there is also the external wrench torque that is applied at the end. We use the Jacobian to transfer this into the force space. And then we simplified our problem such that we only have to learn the external wrench. And as a roboticist, we tend to like a stable controller rather than a pure learning-based controller because we know that we can control these parameters. So then we simplify the problem and we only use the reinforcement learning agent to just learn the high-level wrenches. So in this case, the action space was the forces in the x direction, the torques in the y direction, and the translation of the tool within the z direction, so vertical. And the observations here is a bit more complex than the powder weighing. So you have the end effector state, so the tool tip, so the position and orientation, the estimated external wrench, so the forces and torques at the end effector. And also one of the challenges, and maybe because it's a perception problem, and I think perception is really hard, localizing the material. So how do we get the feedback of a good representation of the material? Again, reward function is quite simple and straightforward. So the main component is how much material is removed. We try to help the agent by giving a milestone reward every large milestones, for example, 80 or 90%, and the contact penalty if it applies too much force. And again, so one challenge is representing the material. So we want the robot to interact with the material in a way that in some cases, we can't model the material. So here you can see a robot learning the scraping task in simulation. Learning crystals are really hard to model. You can't do them. You can't do that in even a physics-based simulator like NVIDIA Isaac. So how we approach the problem, rather than trying to model how the crystals form, we decided to just focus on what we think is the most important aspect for the robot. So how much force it needs to apply to be able to dislodge the material. In this case, we have the particles around the vial surface, and we randomize the different forces it applies by modeling soft and hard materials. And then the robot learns how to apply these different forces to dislodge these particles, which you can see in the next slide. So in terms of the perception part, so again, I think this is one of the most challenging. I don't know if you've seen in the slides, but different materials have different visibility. Some of it is, for example, transparent. So when you start scraping as well, it could look very similar to the back of the vial. So again, I would say this is a very simple method of trying to localize material. And we were not trying to use the most advanced method, but we were trying to help the robot localize where the centroid is, so where is the center of the cluster. And also we want to promote having the robot apply an action on the largest area of material. So even just a simple task like this, it requires detection and segmentation, and of course, the filtering and analyzing the region of interest. But I think perception in robotic chemistry is still a very much an open problem, and I think there is a lot of room where we can improve that. So in terms of how this looks like when we deploy it on a robotic chemist, so as I mentioned, we tended, because it's a contact task, we wanted to rely on the Cartesian impedance to have a stable controller at the lower level. And then we had the higher level RL agent to be able to learn the branches to be able to apply the correct action. This was the first attempt at getting multimodal observation data, which I think also makes it challenging for the task as well, given that it's not an easy perception task. We tried a perception pipeline, so this was really important to help us to localize some of the material, and rather than just relying purely on the force feedback that we get for our robotic manipulator, at least even an approximate estimation of where the region of materials is really important. And in this case, in this particular application, it was really hard to simulate materials, how crystals form. It depends on different aspects. So the longer you leave the crystals to the solvent to evaporate, for example, it can form different crystals. So it's representation of this material is really hard, and modeling the physical behaviors is really hard. So we took a robotics approach where we just wanted to randomize the force that the robot needs to apply in terms of getting the material outside of the vial. So in terms of the results, so we did this trained in simulation, we transferred the policy on our real setup. And I think the exciting part of this project was trying to see how far we can get with different materials. So just to give you an understanding of the properties of these materials, so liquid corn flour is a kind of material that is very elastic. So you would scrape and the tool would slide down the vial wall. Dried corn flour is more like dried pizza dough, and it sticks on the wall. So you need to apply force, and you probably just need to apply a bit of force such that it would crack and then it would slide down. Crystalline salt and sugar are the ones that you need to apply a lot of force, even manually, to be able to do it. And in most cases, if you apply too much force, you might also break the vial. So some people might see it as maximizing the amount of force you're going to apply. It's not exactly like that, because if you apply too much force, you need to make sure you apply enough force such that the material slides down, and that's why the perception feedback is really important. So we compared our method on a baseline, which was just the impedance controller, and our RL-based impedance controller. And we also compared this to human success rate. So in the end, in most cases, I think it's still a hard task, especially with materials like sugar, where they tend to form very hard. That's the only non-chemical word I could explain it as. You need to apply a lot of force even manually. So in that case, I think it was, even for our system, I think the relative success was around 66%. With some materials, like for example, dried flour, the system was doing quite well, so that was around 94% success rate. But what was really interesting in this case was that even just using the RL agent to learn the wrench and relying also on the impedance controller, the performance was better than just fixing the wrench profile for the baseline method. So in the end, I'm a firm believer that a combination of both is a good solution. So there's still, in this task, there's still a lot of open challenges. I think perception, for example, getting a good visual feedback or some kind of feedback on where the material is important. Potential also perception on the force feedback. I think that also depends highly on how sensitive your sensor is and whatnot. And again, I think to me, system modeling is really important. So trying to understand how materials interact with our tools is really important for us to potentially improve this, and whether we could have this improve on human manual scraping, we still don't know, but there are some things that we're thinking about on expanding on this as well. So in terms of kind of summarizing the first, I would say, 2 years of my fellowship, I think robot scale learning is really important for robotic chemistry. Most of it today is still mainly pick and place and moving samples around. And if we want these robot chemists to work closely with human scientists, I think we need to get better scale learning. We need better, I think, for example, in machine learning and in computer vision, there has been a lot of advancement. I would argue that because there's a lot of real world data and good data representation coming from a roboticist, so we need to take this with a pinch of salt. But I think we don't have this, so we need to make sure that we improve on this aspect. The way we've tried to tackle this, and again, the picture on the left is the different materials that it's AI generated, but the different materials that we could potentially want to look at. there's ways that we could potentially improve our robotic simulation environment such that the material properties would represent as close as possible to the real world physical data, so we get better models to help our robots policies to learn in a better representation of the physical environment. And in some cases, we can't do that. So for that aspect, I think focusing and narrowing down what we think is really important for the robot to be able to complete the task, maybe not the most important or interesting for materials chemistry aspect, how do we model the materials, but we need to focus on helping the robotic chemist to interact better with these materials. So I think that's kind of the research part. And I would like to maybe just touch on some of the things which we have started to think about more recently. So I think it's great that we can learn these skills. It's great that we can learn or we can get to deploy these robotic systems. But how do we do this safely and robustly? So again, maybe it's a backward approach, but first we've been focusing on developing these systems. Now that we're in a position that we would like to deploy them, what are the challenges? And I would like to touch on two research directions that we've recently started to work on and think about. So one of it is how can we detect errors when the robotic chemist does them? And what are the kind of mitigation strategies? How do we recover from these? So in a kind of a simple example, one of the PhD students has been looking on, again, rack insertion of well plates. So we have the liquid handler and we have the robotic system picking up these different well plates and inserting them in the liquid handler. Maybe in the video it's not very obvious, but these are designed for humans. So for the robot to complete the task, it needs to lock it into place. And how we've been thinking about it, because even if you do perfect alignment, you cannot do it perfectly. So we've been thinking about correcting the residual error through feedback. So the robot uses a visual language model and gets an understanding of how bad it is, and then it corrects it based on small increments within the task. So this is one way we have started to think about it. Again, rigid bodies tend to be more straightforward than dealing with materials. So hopefully once we advance this a bit more, we can also think about error detection and recovery also with material manipulation. And then again, this is more like new and what we have started to think about. So in a chemistry lab, there's different uncertainties that could arise from different scenarios. And so far, it's been more about deploying the system rather than trying to understand where there could be uncertainty, whether within the environment or within the task. So some of the scenarios that we've been thinking about, for example, when the robot has a vial and it slips, like grasping slippage, how does it recover or how does it go back, and how does it quantify the uncertainty such that the human could potentially intervene? In some cases, robots fill different vials. It's not ideal, but it happens. So what happens in this case? Again, this is some of the earlier thinking that we're starting to do. And I think the thing which we're super interested in, and if anyone has any ideas on this, I'll be very happy to take them. When we have a lot of uncertainty in terms of the material, so we can model some of the properties, but in some cases we can't. So we synthesize a material that we don't fully understand the properties. It's too expensive to characterize. How do we deal with that? And so far it's been mainly in glass vials or well plates, which are kind of standardized equipment. But there's much more different glassware we use in the lab. So, or even like new instruments that we bring in for different workflows. So how do we deal with this kind of unknowns? And again, this is more like an open question for everyone. So how should our robotic chemists at the lower level kind of interaction handle these uncertainties in a scientific lab? So in terms, I think I'm relatively on time. Okay, so I think what I wanted to introduce today was that using embodied AI or robotic systems to accelerate scientific discovery is useful to be able to collect the data for our AI models. For those of you who might be working more on the machine learning side, we tend to have few experimental data, and this is not great for machine learning models and potentially even other large models. So having better robotic chemists is important to be able to collect this data that might be too tedious or too slow to be done by humans. Our vision is that it's not going to be just the robotic chemists collecting this data, but it will be a collaborative effort between the human chemists and also the robotic chemists. And I think maybe like a more advert style, I think the really important thing is working across disciplines. So I think getting to work with chemists, computer scientists, engineers, and different people is important towards solving this problem. So in conclusion, I think if we want our robotic chemists to be able to do more experiments, we need to equip them with new skills. Material manipulation is hard. I think it's still an open robotics challenge. So we need better material representation, potential material tool representation, and better models, whether it's simulation models or getting data into our simulation environments to match and try to minimize the simulation to reality gap. A lot of, even in chemistry, like computational chemistry, there is still a gap between the models and the experimental data. So I think this is something that is important in all aspects. I think doing it in a laboratory automation traditional way where everything is fixed and an open loop is going to be challenging to scale up. So trying to have more intelligent robotic systems is important. And of course, as I mentioned, bidirectional knowledge transfer between different fields is really, really important. So with that, I would like to thank, most of it is work done by my PhD students now. So I would like to thank the people in my group, who actually 2 of them are Manchester alumni, so including myself, that makes 3 of us. And Professor Andy Cooper's group, who supports a lot on the materials chemistry and machine learning methods, and the collaborators, Kevin and Bay, and of course the research funding, Royal Academy of Engineering for my research fellowship, EPSRC for New Investigator Award, and the Liverpool Trust for the different PhD studentships.